Welcome back to ECE 220. You guys have a fair amount to do yourselves. As you know, your lab number 1 report, if you're in Group A, is due today. Your pre-lab for lab number 2, if you're in Group A, is due on Saturday. Group A's lab number 2 will actually be next week, starting on Tuesday and working your way through Friday if you're in Group A. Group B's, after Section E has their lab on Tuesday of next week, your homework number 6 is due for the entire class. Then Group B's lab number 1 report will be due on Wednesday of next week, your pre-lab on the next Saturday. Oh, and by the way, you can apply for advanced standing. Hopefully that will not be influenced by your exam score that you received in this class. It depends on your grades, right? And this particular exam is just one component part, and these lab pieces, remember what happens with your lab? If you don't submit any of or one of those, you lose all of the points for the entire lab component of your grade. So make sure that you do participate and turn in your pre-labs and your reports for the labs. Speaking of efficiency, today we're going to be talking about power and how to try to maximize power at a load, and there's really 2 scenarios that you need to keep in mind. We're going to focus on the second one in this class, but don't get sidetracked by only thinking in that way. And we'll talk then about system efficiency, which is when we are talking about large power levels, big distributions of power, system efficiency, that concept versus if we're trying to transmit information, let's say in a communication system or in a sensing environment, then we might want maximum power transferred to the load. We'll try to make that distinction before we get into that maximum power concept, which is what we will derive. We'll derive what needs to happen with respect to our load relative to the system that's driving that load. How are they related in order to make the load have the maximum power or dissipate the most power? We'll look at some practical applications so that you can be grounded in why are we even worrying about this, or what does this even matter? It does. I'll just state the strategy that we will use in finding the maximum power transfer, and then we'll go through an example. Here are the 2 different scenarios for optimizing. We can optimize system efficiency, that's with large power systems, or we can worry about maximizing the power transferred to the load. Those are 2 different scenarios. I hope that by the end of this lecture, during this class, that you're aware of that distinction. So here, the first one is system efficiency. This is where we get our power, or power utilities. And this is with large power, and this we need to know you will learn in 320A if you take the next class in this sequence, 220, 320A. That's the second half of this textbook. You'll learn in the very beginning parts of 320A this idea of power, single-phase power, 3-phase power. That's this system efficiency. That deals with system efficiency. How do we make sure that the customer or the end product receives power as efficiently as possible? Again, I'm challenging myself with the graphics here, but hopefully you can understand what's going on. We have the power source and distribution, which that's supposed to be a windmill. I know, use your imagination. But here we have then the generation, and we have the transmission. That's supposed to be a high voltage transmission system. That now distributes this power to your home or to an industrial plant or facility. Hopefully, if we're doing our job properly, if we're being efficient, we have very small losses in the generation and distribution of that power. We want to get as much of that power that we create, or energy that we create, to our customer. So we're trying to make sure that the bulk of the power is actually delivered to the customer, and we don't lose a lot of power in the creation and transmission of that energy. That is for next semester. Put that in your memory bank and just realize that there's two sort of scenarios when we're trying to push power from one entity to another. In 320, it's these large generation, transmission, then how do you get that to the customer idea. In this class, we will be talking more about information. When we communicate via radio signals or through wires if we had a microphone, etc., how do we get that information as effectively to the speakers or the loudspeakers? That's this class, and that's what we're focusing on today. How do we optimize our system for maximum power transfer? And this is when we have low levels of power. We may build this system, this amplifier, and we want to make sure that it is delivering the best power that it can to our loudspeakers. Again, this is for sensing, instrumentation, small power levels. That's what we're talking about here. That's the distinction between utility scale power. For this class then, what does it mean when we start talking about maximum power concepts? Let's just create a model. We can now put all of the system interconnections together and aggregate those into this Thevenin equivalent. We now have all of this electronics that we have going on put into a small model with V Thevenin and R Thevenin, and we want to now see what happens when we attach a load to that, a resistor. You know now how to analyze that. What's the load power in this scenario? What's the power at the load? V sub L times I sub L. It's that straightforward. You know that's the power at the load. So if our power at the load is now V sub L, I sub L, we could write that a couple of different ways. In terms of, we could say, well, let's focus on if we had the current, or let's focus on if we had the voltage. And we can do that by applying Ohm's law. If we applied Ohm's law and replaced voltage using Ohm's law, that's IR, then that gives us so with Ohm's law here, we can now say that we have R sub L I sub L squared. And that's the current version of power at the load. We could also replace the current using our Ohm's law relationship and say that we have now V sub L times V sub L over R sub L. Or we now have V sub L squared over R sub L. That's the power at the load. In terms of current at the load and the resistor, the load resistor, or voltage across the load resistor and the load resistor. That's as complicated as it gets. Let's look at some cases. Let's look at some extreme cases. Suppose R sub L in this scenario, we set it equal to 0. What does that do for us? Or how do we maybe refer to that? The load is, what do we call that when maximum power transfer? Sorry, I was distracted by the sound. But what are we doing with the load when we set it equal to 0? What have you done now with R sub L? What does it look like? It's a wire, it's shorted. So the load now is shorted. If we short the load, what's I sub L? Is it small or big relative to other values of R sub L? What is I sub L? V Thevenin over R Thevenin plus R sub L. If we set R sub L equal to 0, isn't the current as big as it's going to ever be with R Thevenin as it is? If we short the load, then I sub L is equal to a max. What's the voltage across the load if it's now a wire? 0. That's a minimum. So what's the power at the load in this extreme case? Our formula hasn't changed. It's V times I. V is 0. So this is now 0. We have a minimum amount of power at the load when we short the load. That's one extreme. What about the other extreme? What if we let the load go to infinity? What does that mean relative to R sub L? What does R sub L now look like if we let R sub L go to infinity? In the first extreme case, we put a wire there. Now what are we putting there? Nothing. We're opening it up now, right? We're removing it completely. Now we have an infinite load being connected, in quotes, to the system or the source. So in this case, the load is opened or removed. Under this scenario, what's the current, I sub L? Now you're virtually erasing that red resistor. What's I sub L? 0. There's no current flowing in this extreme case. I sub L is 0. What's V sub L? Do we know what it is? It's as big as it's ever going to be. It's going to equal V Thevenin, isn't it? So this is now V Thevenin. And what's our power at the load? It's still 0 at this extreme. Now we've looked at two extremes, and both extremes have 0 power at the load. And we're talking about maximum power transfer in this lecture. Hopefully there's something between 0 and infinity that will give us some power at the load. But here are the two extremes. Small resistor and large resistor. What we want to now show is what value of R sub L will actually maximize the power. Suppose we had a generic linear circuit that looks like this, and I've now tried to highlight the piece that we're not going to go through that. Let's just see that for what it is and say, oh, it's some complicated circuit. Let's now make it a little easier to analyze by replacing that with its Thevenin equivalent. So we don't need to know exactly what that looks like. We just need to find its Thevenin equivalent, and that's what we're going to play with. We now have this Thevenin equivalent in place. Let's go through the analysis or the steps that we would need to work through in order to find out what value do we want to set for R sub L in order for R sub L to receive the maximum amount of power. And we know all of the pieces. We know the parts. What's V sub L? In terms of what you see here in the diagram, can you write down a formula for V sub L? V sub L is R sub L times I sub L, correct. Let's now write it in terms of V Thevenin. So that was Ohm's law. So now if you wanted, you could say, well, let's get rid of I sub L or rewrite I sub L in terms of V Thevenin. You know I sub L is V Thevenin over the sum of R Thevenin plus R sub L. Or we've now just re-derived the voltage divider expression. We now can say that V sub L is R sub L over R sub L plus R Thevenin times V Thevenin. And when we were re-deriving that, we actually reminded ourselves of what I sub L is equal to as well, in terms of V Thevenin, R sub L, and R Thevenin. I sub L we could find, if we know V Thevenin, we just divide that by R sub L plus R Thevenin. We're wanting to maximize power. We have V, a formula for V. We have a formula for I, and we know power. Power is V times I at that particular element. Let's now build that. The load power is now V sub L times I sub L, which is, if we put these pieces together, we have R sub L upstairs. We have the sum of R sub L and R Thevenin, two factors, so we square that, and then we have V Thevenin multiplied together, or we have V Thevenin squared. This is now our expression or formula for the power at the load in terms of V Thevenin, R sub L, and R Thevenin. We're assuming now that we know V Thevenin and R Thevenin. We're trying to find R sub L. And the R sub L that we're trying to find, we're wanting to find the R sub L that maximizes that formula. Maximizes. How do we maximize something, or where did you learn about maximization? Calculus. Remember calculus? Can't forget that, right? You have nightmares about calculus. Well, this is one way to use that relationship you have with calculus and say, okay, if I have this formula and it is dependent on a variable, r sub L, I want to now maximize that formula with respect to r sub L. And I know V Thevenin and I know R Thevenin. Those are considered constants. How do I maximize this P sub L? And now you're trying to make your math instructor proud, right? What do you do, or what would you have done if you were taking a math class and you were given this formula and they said maximize this with respect to r sub L? Wouldn't you differentiate that formula with respect to that variable, which in this case is r sub L, and then what do you do? When do maximums occur? What are you looking for? Are you looking for a derivative? Are you looking for an integral? What? I just differentiated, so I'm obviously looking at the differential. What happens to the derivative at a maximum? It's 0, isn't it? Now if that curve is peaking and we are wanting to know where is it hitting the maximum, then the derivative, the slope, is going to be flat at the maximum, at the peak. So we set that derivative equal to 0. To maximize this, we're going to take dP sub L, dr sub L, and set that equal to 0, and then solve for r sub L. And I'm going to let you do that tonight or this afternoon, maybe right after class. Take the derivative of that with respect to r sub L and set it equal to 0 and solve for r sub L in terms of V Thevenin and R Thevenin. And what are you going to find? If, in fact, you set R sub L, the load resistor, equal to the Thevenin resistance, you're going to maximize the power that you can distribute to your load. Again, this is in a instrumentation or communication scenario. Not in a big industrial plant, because you don't want to waste half of your power in the plant that you're trying to give to your customer. This isn't going to be what you use when you're in an industrial or utility environment. This is what you use when you have, well, we'll give you some practical applications in just a minute. But here is the picture. We had one extreme when R sub L was 0, the power, P sub L, was 0. We had the other extreme when R sub L went off to infinity, P sub L vanished. And right at that Goldilocks moment, P max, or P sub L max, happens when R sub L is equal to R Thevenin. This is now P sub L max. So the maximum power transfer occurs when R sub L is equal to R Thevenin, and we had the formula for PL. What is now P max when we replace R sub L everywhere with R Thevenin? R sub L was in the numerator, so we put it up there. It was also in the denominator, along with R Thevenin, and then we had V Thevenin squared. But we can simplify that. Now we have R Thevenins in the top and R Thevenins in the bottom. We have 4 R Thevenin squared downstairs. We have R Thevenin upstairs. One of those R Thevenins can cancel, and we're left with, at this maximum power condition, we could compute it by simply taking the Thevenin voltage, squaring it, and dividing by 4 times the Thevenin resistance. I guess we were feeling mathy, so let's introduce a theorem. A maximum power transfer theorem. Maximum power is delivered to the load when R sub L is equal to R Thevenin. We derive that, or you will tonight, to convince yourself that R sub L is equal to R Thevenin. What are some practical applications? A big one is impedance matching, and that's used routinely. In fact, it's built in to your oscilloscopes in the ECE 220 lab. You turn it on, and the default setting is it's expecting a 50 ohm load. Actually, wow. Correction, your function generator. What you are creating these signals with, it's expecting to see a 50 ohm load when you turn it on. So now you have to tell it, if you don't want it to be doing that, it's going to set its internal impedance to be 50 ohms so that it matches the load that it's expecting is 50 ohms. That's typically where you might see this. So you need to remember, if you don't want twice the voltage at your terminals that you are now having coming out of your function generator that you expected, you may have to change that default setting. What about another practical application? You're talking into a microphone. That microphone might have an output impedance of 300 ohms. Well, to make that information, that data, that sound that you're creating with the with your voice into the microphone, to make that sensor as effective as possible, you would want the input impedance to be matched. Your amplifier input impedance needs to be the same as the microphone's output impedance. And on the other side, now that you've modulated that, you've put it to a higher frequency, now you can transmit it as a radio signal so that you can now tune that into your dial. Now you want to match the RF, the radio frequency amplifier's output impedance, to the impedance of your antenna, and that might be at 200 ohms. This impedance matching, this RL equal to R Thevenin, occurs a lot. That's what I'm trying to illustrate. One more. How many people like to listen to music? What used to be, I don't even know now what you have in terms of your speakers. Now all you have are earbuds, right? But if you had loudspeakers, a lot of times those have an 8 ohm impedance. And because of that, your amplifier now wants to be matched to that so that whatever you're generating with your amplifier, you now are effectively maximizing the power that you're presenting to your loudspeaker. So you have an 8 ohm output impedance of your amplifier, and that now is matched impedance-wise with your speakers for maximum communication capability. Another application of impedance matching or maximum power transfer. What's going to be our strategy? Here is our strategy. Anybody here, when I see this written this way, it reminds me of when I was in your chair a long time ago. Has anybody seen engineering tablets or engineering paper, engineering pads? If you don't, come to my office hours. I have one, I think, somewhere in the office I can show you. It's green, and it has grids, and you can write on it. Well, when I was in your shoes, I had to always do my homework on this engineering pad and turn it in. There was a very prescribed form. We had to state what is given. Then we had to state what are we trying to find, and then we would say, here's my solution. Throwback. Here I've implemented that strategy for maximizing power transfer. What are we given? We're given a complicated circuit. We find its Thevenin equivalent at terminals A and B. And we want to now find what's the best value for that load resistor to maximize the power transferred to it. So we reduce our circuit to the Thevenin or Norton equivalent, and then we simply set the load resistor equal to that R Thevenin that we communicated or that we found. Not that complicated in terms of a strategy. Just find the Thevenin equivalent. That's the hard part, maybe. That's where you might have to do the work. But once you found your Thevenin equivalent, then you simply set your load resistor equal to that Thevenin resistance. What are you going to remember after today's lecture? For maximum power transfer, R sub L is equal to R Thevenin. Let's see if we can work through an example. Here is a circuit, and somebody says, I have a resistor, R sub L, connected between node A and B. That's what I'm considering my external load, and I want to now pick that, the value of R sub L, so that the maximum amount of power from the rest of the circuit, from the rest of the system, is delivered to that load resistor. I want to find what's the magic value, what's the Goldilocks value of R sub L. What's the just right value? That needs to be R Thevenin. Do you see R Thevenin from this circuit? Give me a break. Well, we're going to compute it. How's that? You have the skills, you have the technique to do that. So let's now, here's our strategy. We're going to adjust R sub L for maximum power transfer to that resistor R sub L. So the first thing we're going to do is what? If that's what we want to make or set R sub L equal to R Thevenin, now what do we do? if you don't know today, you definitely want to know by the second exam how to do this. You need to know it by homework 6, right? So what are we doing if we're trying to find the maximum power to R sub L? What's the very first step? Just get rid of AB, or get rid of R sub L and find the Thevenin equivalent to that circuit by some strategy, right? So we have to figure out how we're going to analyze this circuit. So first, let's just write down what we said. Let's go ahead and say we are going to remove the resistor R sub L and find the Thevenin resistance of that circuit. And now you're saying, well, now what do I do? Do I do node voltage analysis? Do I do mesh current analysis? If we did node voltage analysis, what would we have? Well, now we have that crazy 1K resistor right there, which is kind of problematic. But if we did something, let's say here, then that would be a given, wouldn't it? So we wouldn't have to solve for that node voltage, but how many other node voltages or essential nodes do you see? Remember, we've removed AB, so all of those are the same node. Here's a node, and here's a node. So we do have 3 unknown node voltages to solve for if we did node voltage analysis. We're doing a little preliminary thinking, some thought. Well, let's now look at the other strategy, which is to do mesh current analysis. What would that involve? Remember, we don't have that in place. That's now removed. So now we see 3 meshes. So it's really not, it's sort of 6 of one, half a dozen of the other. Which of these we use? We have 3 unknown mesh equations. Or I'm sorry, 3 unknown mesh currents from our 3 mesh equations. Let's just go ahead and do mesh current analysis. A lot of people like to go in circles, right? Or that's not what I should have said, but we're going to go in circles to find the solution. Let's go with MCA. Resketching, accounting for opening up the connection between nodes A and B. Oh, and I had an I beta here, I think. And I had a 10K here. I had a 2K here. The dependent source. And I actually had a resistor in that branch. And I'm now trying to find that voltage. This is now A and B, and with mesh current analysis, I could say, okay, let me now do a mesh current analysis. Here is mesh current 1, mesh current 2, and mesh current 3. If I find I1, I2, and I3, am I going to be able to calculate my open circuit or my Thevenin voltage? What is VOC? VThevenin. But what's VThevenin in terms of mesh currents? I need that to be positive from top to bottom, so I need my net current going down from the top to the bottom, and the current going down through that 10K ohm resistor is a combination algebraically of I1 and I3. It's I1 minus I3 is the net going down, whatever those end up being. VOC is then 10K times I1 minus I3. Now I'm saying that if I can compute I1 and I3, I can get half of my problem solved because I need V open circuit, and then I need what? I'm doing the direct method of finding R Thevenin. I'm finding V Thevenin, and then I'll need to find I short circuit. So I'll short A and B in the second piece of this analysis and compute R Thevenin from V Thevenin over I short circuit. What else might I need to know? What is I sub beta? That's a constraint. Is I sub beta minus I1? What is I sub beta? It's the current through that 1.5 K ohm resistor, and it's going. I've labeled it now to be going positive from right to left. That's now the net of I sub 2 minus I sub 1. If I need to replace I sub beta anywhere, I can say that that's going to be I sub 2 minus I sub 1. Let's now write these expressions, the mesh equations, for what we've now identified with the different mesh currents. Mesh number 1, do you see it's minus 120 plus 1.5 K times what current? I'm now going from left to right. I1 minus I2, 10K times I1 minus I3 plus 1K times I1. That's my first equation. I have minus 120 plus 1.5K times I1 minus I2 plus 10K times I1 minus I sub 3 plus 1K times I sub 1, and that's equal to 0. That's my first KVL written for mesh 1. How many of these am I trying to find? I have to write 3 of those because I have 3 unknown mesh currents. What about mesh 2? That's 1K I2 plus 2K times I2 minus I3 plus 1.5K times I2 minus I1. Those all get me back to the start, so that's equal to 0. Pardon? The question was, are we going to be using mesh more often than node voltage analysis? I'm not going to answer that. You can choose which one always works. Node voltage. So sometimes you can't use mesh. When can you not use mesh analysis? When can you not use mesh current analysis? When your circuit is non-planar. You have to have a planar circuit. You have to have these meshes in order to do mesh current analysis. Node voltage analysis always works. I've found that traditionally students prefer mesh current analysis. It's easier. I'm sorry, I shouldn't say that. It just appears more straightforward to the majority of students. But you don't have to use it, and you need to be very comfortable with doing node voltage analysis, writing KCL equations. Here you're writing KVL equations. Let's do one more. If we start in the lower left in mesh 3, we have 10K times I3 minus I1 plus 2K times I3 minus I2 plus 5,000 I sub beta plus, we can't forget the bottom, which is 500 I sub 3 equals 0. And now, luckily, we remembered that I sub beta was, in fact, I sub 2 minus I1. We can plug that in, and now we have three equations in the three unknowns, I1, I2, and I3. We can solve those for I1, I2, and I3. That ends up being 99.6, 78, and 100.8 milliamps. So that now we have enough information to find VThevenin. VThevenin was the 10K times I1 minus I3. Plugging all of that in, we end up with minus 12 volts. If we're running laps, we've completed one. We've completed one of the two steps of this process. Now what do? We found VThevenin. Now we need I short circuit in order to compute RThevenin. And in this case, when we short terminals A and B, this 10K ohm resistor is now effectively shorted out. Or we now have our circuit looking as follows. We want to find that branch current. And now how are we going to find that? This is now node A and B, and we've shorted it out. Again, we could do 3 meshes, but in fact, if we look at this, because we've now sort of shorted one of these out, we really only have these 2. If we now said, well, let's make our reference node that node that's shorted out and call this V1 and V2, we can compute that value because it's just separated by a source, as is that one. And we can now write KCL. We can do node voltage analysis at those 2 nodes, V1 and V2. We'll take that offline, do that, and compute our R Thevenin, and then we'll have enough information to find R sub L, which is equal to R Thevenin, and compute the maximum power.